These maths teachers are taking part in a project that's looking at the ways ICT can help with hard-to-teach secondary maths topics. Leading the project is Alison Clark-Wilson of the Mathematics Association and her colleague, Professor Adrian Oldknow.
Everything else changes on the screen.
The group has come together to share resources they've developed and used with their own pupils. What each topic has in common is the use of ICT to tackle a traditionally tricky topic.
I've been looking for some time at circle theorems and using ICT to support that.
Ruth's Circle Theorem project uses dynamic geometry software, which allows pupils to make and manipulate their own geometrical constructions.
This is the one we liked, didn't we? You know, they've done quite a lot there, and I'm particularly interested with these students to look at geometric reasoning and also proof.
Before she tried this topic with her pupils, Ruth explained her plans to project leader Alison Clark-Wilson. One group of pupils would have step-by-step instructions for what to construct and what to investigate. The second group would have a set of cards with fewer instructions.
So this one, when they come, it just says construct a circle, construct a triangle whose vertices all lie on the circumference.
Yes.
Make some conjectures about the angles you've created.
And the third group would have just the text of the theorems themselves to work from.
This is going to be a real experiment. Let's see what happens
yes.
to these students. So, number one says, show that the angle subtended at the centre of a circle is twice the angle subtended at the circumference.
Yes.
So their focus is very much on proof.
Yeah.
Ruth hands out the prompt sheets and cards for her Year 9 pupils to get started.
From the File menu, choose New Sketch. Construct a circle. From the Construct menu, choose Line.
They've used this software a few times before and have done some work on the properties of triangles.
Now you've got to construct an isosceles triangle with the odd angle at the centre.
The odd angle of the centre?
Yeah, you know how to do that.
Right.
Click that one.
Where did you start?
The students have set up the software to display the angles in their triangles on the screen, and it's not long before they come up with some conjectures.
Every time we move the C angle, the other angles all change.
When you move the points around the circumference, all the angles change in the triangle when it's in a circle. Apart from...
What's the one that stays the same?
That one.
Only two change at a time. So you can write that down.
It was asking about, like, if you made a triangle, what the angles would be if you moved points around the circumference. As we did there, we found out that B would always stay the same and A and C always change. But A and C, when you add them up, they'd add up to 90 degrees. And B would always be at 90 degrees.
The angle of C on this side of the chord
Is 45.52 degrees.
Right,
all the way around.
Yeah.
But when it goes below the chord,
Yeah.
it changes to 134.48, which both the angles add up together to create 180 degrees.
Fantastic.
The pupils working on the orange cards begin to devise some actual proofs.
Yeah, we cut it in half, so there's two isosceles triangles.
Ah, right, interesting.
Because we've been learning about isosceles triangles.
So isosceles triangles are pretty
Very
important.
important.
Ah.
And the measure angle.
I know you want to measure some angles. Okay, I'm going to leave you to that one. I'm going to come back to you and see how you get on.
Measure. 46.
Should that be equal to that?
Yeah.
We'll just make sure.
I'll cut it into two to make two isosceles triangles on both sides.
Good.
And that means that the two opposite angles should be the same size.
Good.
And there should be one odd angle.
Good.
So I worked out the middle angle.
Yes.
And from that I got the other two angles. So I divided that by 2 to get the other two angles.
Right.
The angle in CDH, we were trying to prove that that is twice as big as the angle in here, CFH. And what we did was we clicked on the 2 points, F and D, and drew a line through. So we have both angles.
So they're isosceles triangles.
So we created 2 isosceles triangles. So these 2 angles added together, the 2 similar angles, must equal
exterior angle.
the exterior angle here. So if we So this is exactly the same isosceles triangle. It's another isosceles triangle because it's got two radii. So we've got two of the equal angles from each triangle. So this must be two. It must be double what they add together to equal that. And it's asked us to make some points going to the middle from angle A and C.
And to measure.
And to measure them.
And then it's asked us what do we notice. And we notice when we move like the angle B, it's at 70, say here, it's at 72.85 degrees.
How would they have tackled this project without the geometry software?
Normally, you can't really move angles on a piece of paper, really. It won't really do much, will it? So a computer using this software is really good because it lets us experiment. While it's not that hard, but you can learn so much out of it.
First you set up the circle, then you put 2 points on the circumference of the circle, construct a line, select a midpoint on the chord, then you select the midpoint and the chord and construct a perpendicular line that sends a line going through the centre of the circle. Wherever you move the points on the circle, the perpendicular line will always cross through the centre of the circle, and there'll always be a right angle on the point and the chord.
Clearly, the students found the software very useful for this project, just as their maths teacher had hoped.
Do you think that using the software enabled them to do more maths or enabled them to go further with circle theorem than you might otherwise in Year 9, Ruth?
Oh, definitely, yes, I think so. And I think it allowed them to go further in the sense they got freedom and they weren't sitting working through a textbook getting stuck,
yes.
Which is what you might expect if they had this sort of thing.
Yes.
They were able to try things out and in a reasonable amount of privacy, actually, in the sense that, you know, they weren't sitting in front of the whole class doing things. And I think definitely they've got... I mean, I wouldn't normally perhaps even start on circle theorems in Year 9.
Yes.
But I just thought it'd been interesting to try with them and see what they could do.
Yeah.
And I think they've certainly gone beyond an average Year 9 at this stage.
I decided to go away and look at one of the things I thought was hardest to teach, which was solving 3D geometry problems.
Ashling's hard-to-teach project involves using 3D geometry software to help her pupils visualise and understand the properties of three-dimensional shapes.
They were the side length we had.
Before she used the materials with her pupils for the first time, Ashling showed Professor Oldknow what she was planning to do. He's an acknowledged expert in how to use this software.
One of the most important features of Cabri is the fact that we can actually open up a shape.
Is that something they've tried before, or will it be something quite new when you do that?
Some of the students should have done this before when studying nets.
Right, OK.
So we're looking at the fact that this is a right-angle triangle.
What is so hard for pupils about working in 3 dimensions?
The hard-to-teach element is the fact that we're no longer dealing with a rectangle or just any old 2D shape. And when you're presented with something like this, people find it very difficult to visualise breaking down the object and opening up the object in their heads. And I think when they see it on something like Cabri, it just changes their thinking process a little bit.
It's so hard to teach, it's usually not done. It's usually cut out. I mean, the amount of 3D work that's actually done in the secondary school compared to the preparatory work that's done in primary school is pretty tiny. It's usually omitted because it's actually also very difficult to test. On the other hand, we all function in a 3D world.
The whole idea throughout this lesson is that students will connect, that you can use this to help you while still being able to solve the problem by yourself with a pen and a calculator if you have to. And I suppose you have to keep that in mind, and that's what teachers would often be worried about, I think, because they think that when you start using something like this, you throw away other methods and other uses, but that's not, it should complement that work. And the problem I have for you has got to do with a box.
In the lesson with her Year 9 group, Ashling introduces a 3D problem.
Okay, this is Joey's box, and Joey is having a bet with his friend Jasmine. And the bet is about what is the longest stick that would fit into this box. So what I want you to do for a moment, I'm going to pass some boxes around, is have a little chat with the people around you and try and figure out what you think the right answer might be for a box like this.
So how long do you think that this is, like the length of the rectangle is?
So like we could put a line through it. We work out the length of this one, then we know like how long the stick can go in there.
We can use Pythagoras. Measuring it that way is going to have a longer stick than measuring forward like that. So we're going to measure it that way to see how long the stick can be.
They then look at an interactive version of the same box made on the software.
Thank you very much, Vivian. Okay, so Vivian has actually opened up the box so that we can see inside of it. This line, which is one of the sides of our cuboid, is 8.2 centimetres, whereas the diagonal is actually 9.9. Right, is that the longest stick that could fit in, do you think, into this box, that 9.9 centimetres? Do you have another idea for me?
You could measure from E to C.
From E to C, right. So then you're actually finding the diagonal from the top vertex to the bottom vertex of the cuboid. So if we measure the length of that segment, 11.5. Well done. I'm going to rotate the shape so we can have a look at it from different angles.
Is it triangle?
Does anybody have anything they want to mention? Denai?
Yeah, you can see a triangle inside of it. I think it's from points E, G and C there.
So you want me to go from point E to G to C. Okay, let's rotate that and have a look at it. So if we don't know this length here, how can we work out what it is? Elise?
To find the length, you could use Pythagoras theorem.
So we know that, for example, this side is 5.5 and this side is 8.2, so we can work out what EG is. Once we know EG, we already know that from G to C is 6, so we can use our value from EG and GC to find the length of the longest diagonal. So in fact, in this problem, we have to use Pythagoras twice. Okay? I want you to try that out with the person beside you now, please.
Although the software can give all the measurements automatically, Aisling believes it's important for pupils to back up what the software can do with the written methods they're expected to use in the exam.
We're trying to work out the pink triangle at the top first. Find the hypotenuse. So it's 5.5 and 8.2.
Yeah, 5.5, 8.2, and the hypotenuse
equals C squared. 8.2 squared is 67.42.
What I want you to do now is on your laptops there's a folder called 3D Geometry.
The next task asks pupils to use the 3D software to work out the angle between the diagonal of the cuboid and its base.
So you're using open polyhedron, and now you can pull down the net. So what should you do first, do you think?
find a segment. Do a segment.
Super. So go to the segment tool for me. From A